Hi, we're going to learn about filters and frequency response for circuits. So what we're going to do is figure out the transfer function and then what type of filter this is and calculate the center and minus 3 dB frequencies of this circuit. Okay, so this particular task is to find the transfer function, also known as the gain, which is the ratio of the output to the input voltage phasors. And these things themselves could depend on frequency. So everything here is really a function of frequency. And the output to the input is going to be from a voltage divider, the parallel combination of this RLC in parallel, RLC, and the R2 that we've got up there. So we just need to figure out what that RLC in parallel is. And Z pair is equal to then 1 over ZC plus 1 over R1 plus 1 over ZL. And all we're doing that's different is to keep everything a function of frequency. So now this is 1 over J omega C, that's the inverse of the capacitive impedance, plus 1 over R1 plus 1 over J omega L. Okay, and we could substitute that in to our transfer function. H is equal to, before we do that, maybe it's going to be a little bit more clear to kind of divide by Z pair here so that we can just multiply by this instead of multiplying by the inverse of this in the numerator and denominator. So that means we'll have this term, and then we can clean that up a little bit. So we'll get an R2 over R1 for the real part, and the imaginary part, let's factor out a J, and then we'll get negative 1 over omega L for that. Okay, now this is the transfer function. We're done. We've got it. That's the transfer function. We just need to substitute in, and then we've got our information there. To figure out what type of filter it is, we can look at the form of the transfer function. So we want to figure out, is this a low pass? Does it only allow low frequencies through? Is it a high pass, only allows high frequencies? Does it only allow some narrow band in the middle, a band pass, or does it only stop some narrow band in the middle, allow the other frequencies? That would be a band stop or a notch filter. So to figure that out, we can look at the transfer function, or we could maybe look at the circuit itself and use intuition. Let's try and do both. So for the transfer function, we'll consider the magnitude of this, which would be 1 over the root of the real part here squared. So that'll be 1 plus R2 over R1 all squared, plus the imaginary part squared. Oh, and actually, you know, the imaginary part, just looking at it now, I think I dropped an R2 there. Yeah. Sorry, R2. There you go. Okay, so now that R2 is securely back in position, we've got J canceling out as we take the magnitude of this. We've got an R2 multiplied by omega C minus 1 over omega L, all squared. And yeah, so you see the maximum gain is when we have the minimum in the denominator here. And the minimum, this is not a function of frequency. This part's a function of frequency. And we'll get the minimum when we have this thing that can actually go to 0 going to 0. So the maximum gain is at this equals 0, which means omega is 1 over root LC. So that's the solution to that. This is called resonance, aka the center frequency. And the reason for this being the center frequency is that this gain magnitude actually goes to 0 at either DC, really low frequencies, or really high frequencies. To see why that is, if we go with omega towards infinity, then the denominator blows up from this omega term here, And, this one goes to 0, but that doesn't matter. So we have infinite squared. So the whole thing is infinity. We're dividing by infinity and we get 0. Okay, so no gain at omega going to infinity because of this omega c, the capacitor term. And we also have no gain as omega goes to 0 because of this omega L. That's from the inductor. Coming back up here, as frequency goes to infinite, the capacitor acts like a short. And that means that we don't have anything showing up across the output because the capacitor just shorts it out. So we've got a voltage divider between something and 0. Taking the output across the 0, we've got 0. At really low frequency, the inductor acts like that. It shorts out the DC response, so we don't have any of that showing up. But at somewhere in the middle, the capacitor and the inductor cancel each other out, and it's like they're not even there. We get a voltage divider between just R2 and R1 in that case. So that's where we have 1 over 1 plus R2 over R1, which, note, is actually a rearrangement of the common voltage divider formula there. So R1 over R1 plus R2, exactly the same output that we would get if L1 and C1 in parallel were canceling, which is what they'll do at resonance. So this ends up being a bandpass filter because it allows a frequency band in the middle range to pass through while shorting out the really low and the really high frequencies. All right, the last thing is the minus 3 dB frequencies, and these are where the magnitude of the gain has reduced to 1 over root 2 of its maximum value. So the reason for that is because this is the gain in the amplitude. So the point where the minus 3 dB frequencies occur are going to be where the amplitude gain has gone to 1 over root 2 of the maximum amplitude gain, because that's the point where we're going to have minus 3 dB, also known as 0.5 of the maximum power. All right, so let's substitute the numbers that we've got in the problem in. So with the inductance, capacitance, and resistance that we had, we can calculate the transfer function. We can clean that up to make it obvious what to look for the 3 dB frequencies. Before we do that, let's solve for the center or resonant frequency, 1 over root LC, and that's 503 hertz. The minus 3 dB frequencies are where we reduce to 1 over root 2 of the maximum amplitude, which in this case is 0.5. So this factoring has worked out quite nicely. We just need to know where this thing is equal to 1. So that'll be either where the inside is equal to positive 1 or where it's equal to negative 1. If we're looking for the positive frequencies that do that, then we can use the solve command or just quadratic formula and figure out that the frequencies are 2488 rad per second or 488 rad per second, which are 3261 hertz or 77.7 hertz. And the bandwidth is the separation between these, which is 3183.1 hertz. And that's quite a lot higher than the lower of those frequencies, because this is quite a wide filter. So we have, we can still kind of define a quality factor for something like this. We end up with 0.158 by taking the ratio of the central frequency to the bandwidth. But we do have to be a little careful with quality factor. Not everybody uses the same definition of the quality factor, especially when it's quite low. The different definitions can start to diverge. Although this is okay for this particular kind of filter, for other filters which don't go off to 0 in the stop bands, then this definition would not quite work for that. Anyway, here's a way to get an idea of what the pass band looks like for this filter, and that's with a log-log plot. So we've got log-log plot, so log on the frequency and log in the amplitude of the magnitude of h. And this allows you to figure out what the gain looks like versus different frequencies. Although it's not very good for figuring out the minus 3 dB frequencies, because you kind of got to look and figure out where this reduces to 1 over root 2 of where it started with. That's a little bit tricky to see on this graph without plotting it by yourself. So Bode plots are a little more convenient for that. And this is something that you can do by now just using a semi-log plot. So you plot logarithmic in frequency and linear in the vertical. But the trick is, instead of plotting the absolute value of h on the vertical, you just directly convert it to 20 log 10 of the absolute value of h. So you've got it in decibels right away. Now we've got minus 6 dB when we have the gain of 0.5 at the start, and that ends up with minus 3 dB more, so minus 9 dB total when we're at our minus 3 dB frequencies. Remember that those 3 dB frequencies are relative to your maximum gain, which in this case is at an absolute decibels of -6. Right. So another thing you can do is plot the argument of h to look at the phase. So we've got a phase which is changing from limiting towards positive pi by 2 at the really low frequency end and negative pi by 2 at the really high frequency end compared to the input. So when the inductor is dominating things, then we've got negative 90 degrees for the output voltage compared to the input. When the capacitor is really dominating things, we've got positive. Oh, wait, hold on. When we're at really low frequencies, the inductor is when that is dominating things. And that's where we end up with the positive 90 degrees for the voltage relative to the voltage of the input. And that kind of makes sense because the voltage here versus there is going to be determined by the current, and the voltage and the inductor has to lead the current through it, and vice versa for the capacitor, which explains what's going on at those high frequency points. Okay, now so in summary, we've got the phase at the high frequency and the low frequency determined by the inductor over here, inductor at low frequency and capacitor at the high frequency. And another thing to note is that the phase shift at the 3 dB frequencies is a little bit hard to see from this plot in particular, but it's kind of half. This is basically like a straight line, and so we end up with, not surprisingly, a 45 degree phase shift in either direction at the 3 dB frequencies. So that's another thing that you can look for, and we're going to make use of when we're looking for them in Multisim. So in conclusion, we figured out the transfer function by keeping the frequency in our complex impedance and doing the same kind of voltage divider stuff we were doing with AC network analysis. We figured out what the type of filter was by looking at the transfer function. In this case, it's a bandpass because it has a gain that goes to 0 at either frequency extreme and is not 0 somewhere in the middle. The resonant frequency is the point of maximum gain. And we found out the 3 dB frequencies by looking where the gain drops to 1 over root 2 of what the gain was at resonance. Now we can go and simulate this circuit and see if we get the same kind of results as we did. So just to summarize, the main results that we found were that the center frequency is at 500 Hertz, and we found cutoff frequencies at 77 Hertz and 3261 Hertz. We found a central gain of 0.5, and yeah, I think that's it. We found a frequency response which looks generally like this, and we found a phase response that looks like that. So let's see if we have the same kind of stuff over in Multisim. There's a few different ways to get this in Multisim. You can do the regular old parameter sweep and then oh, I guess no, that's not right. Sorry, you can't do parameter sweep. You can do an AC sweep, which is to sweep the frequency. And what we'll do is, yeah, okay, so 1 Hertz to 10 gigahertz, and we are going to output I think that net is V1, so let's see. Okay, so let's double check that we have the right net name over there. Net name 1. Okay, yep, that's right. So we're looking at the right output. Probably the range is not so great right now, but we do have roughly the right kind of shape for the frequency range that we actually used here. So we've got a cursor here that you can use to sweep around. So if the cursors are are not on originally, then you can just move them around with your you can activate them with this button. So that's the show cursors, and that's separately activated for each plot. So just sort of click in the plot area and then say show cursors, and you can see, well, we've got a Y of around 500 milli, so 0.5 at the max. That's the gain, and we can look for where the gain would drop to 1 over root 2 of that value. And so root 2 is 1 over root 2 is 0.707, and so that times 0.5 should be around 0.35 or so. So we're going to be looking roughly for that, which tells you the frequency where that happens is about 76. So with a little bit less rounding, you would do a little bit better than that. But still, that's pretty much what we found. We found 77 hertz analytically, and now we've got 76 hertz with Multisim. On the other side, we've got, now looking at the Y2 for that cursor, we are looking for where this is around 350. And if it's too hard to be this precise, then one thing you could do is go back and reduce the frequency range. And here we've got, this is 3.2K in terms of the frequency. Let's see what we found again. So that was, yeah, 3261 hertz and 77.7 hertz. So that's pretty good. We found our 3 dB frequencies. We found the center point. So central gain looks like it's about there, which says it's looks like 465 hertz. Now this one's pretty tough to track down, yeah? Using the gain plot, you'd have to, because we're looking for the peak of a curve which is really flat. So you can look at the Y value here and look for where this is 0.5 or as close to 0.5 as you can get. And this time we got 522, and that is okay. It's not so great compared to the frequency we were expecting. Another thing you can do is look in the phase plot. So in the phase plot, at the first point, so at the minus 3 dB frequency there, we expect a 45-degree phase shift, and we expect a 45-degree phase shift on the other side too. So minus 45, and now we've got our 77.7 hertz and our 3.28K on that side, and you can look for where the phase shift is a 0 to see where the resonance is. So that's pretty good. We got like a 1 degree phase shift there, and that's at 458. Again, just pretty hard to drag these into the exactly right range. But now this one, I got it pretty close on. So that's at 0.05 in the, so negative 0.05 degree phase shift. And we've got a, and that's at the frequency 505, which is really close to our analytically determined one. So there we go. That's how you use this AC frequency sweep in order to determine the outputs in Multisim. Another technique you can use is to go back to interactive, and we actually have a measurement tool which can determine what the which can determine frequency response as well, and that's the Bode Plotter tool. So that's I'll put this over here so you can sort of see where I'm clicking. So that's this one, and now we'll go and drag this in. Whoops, guess I placed another one. We don't need two of these. And what we'll do is we'll define what you want to be the input and what you want to be the output. And then you can just run the simulation in interactive mode, and it will plot for you the magnitude and the phase. So you can set up exactly the ranges that you're looking for. You can move around cursors here, and it reports it directly in decibels, knowing that that you're going to be dealing with this from trying to do like Bode Plot type stuff. You can change around your ranges here. You can also change the vertical range over here, so we can raise up the minimum range and get a nice picture of the Bode Plot there, looking for where. So now where the 3 dB points are, we would see here we're at minus 6 dB at the top. And we could, again, narrow this in to try to look for where that resonance is. Or you could look on the phase plot. Wow. So let's just go from, how about negative 45 degrees to 45 degrees. And so right in the middle there, 505 hertz. Great. And we could also narrow the range of frequencies to get closer to the ones that we're looking for. Okay. So magnitude plot. There's our 505 hertz. If we want our 3 dB frequencies, we're going to look for now where we've gone to 9, and there's our 77 on that side, and looking for 9 on this side. That'll be about 3.2K. Okay, so there's how you use two different tools to determine what the frequency response is of filter circuits using Multisim. Thanks for watching.